Hello, dear students. In this video session, I will be explaining you about hydrogen bonding. Just so you know that hydrogen bonding is a type of dipole-dipole intermolecular forces, and hydrogen bonding is the strongest type of intermolecular forces that we learned so far. So the weakest one was London dispersion, then comes dipole-dipole, then comes hydrogen bonding. And we know that what was dipole means. Dipole means this is a permanent dipole. One end is negative, and another end is positively charged. And dipole means it is we have the intermolecular forces between those two. So what makes hydrogen bonding different? Three elements, which are really good electronegative elements: fluorine, oxygen, nitrogen, that should connect to hydrogen atom. So in one site, we should have an hydrogen atom, and it should be connected to either fluorine, oxygen, or nitrogen. Please don't forget these three elements. So let's take a look at hydrogen bonding in water. We know that we have hydrogen in one side, and you see this hydrogen is connected to one of these three: fluorine, oxygen, or nitrogen, and it should be connected to intermolecular forces to either fluorine, oxygen, or nitrogen. You see, this hydrogen that has oxygen is should be connected to another oxygen, fluorine, or nitrogen atom, which is called hydrogen bonding. So don't forget these three elements. You see, in both sides we should have these elements. This is the overall. Let's look at a few examples in here. For example, water molecules, we have discussed it. We have hydrogen that should be connected to oxygen. Let's take a look at this one. Hydrogen is connected to nitrogen, hydrogen connected to fluorine, hydrogen is connected to oxygen. You see, we have these either fluorine, oxygen, or nitrogen. That hydrogen is attached, and these hydrogen should be again either connected to oxygen, nitrogen, fluorine, or again oxygen. So you see, in both sides we have fluor, nitrogen, nitrogen, oxygen, oxygen, etc. Please don't forget those. Let's go through these slides too. So we know that also these molecules, please don't forget that they also have London dispersion forces too. Because in all molecules we have London dispersion, but as we have hydrogen bonding too in these molecules, it makes them much more stronger, so they have higher boiling point. So what do we see in here? We know that hydrogen bonds are the strongest form of intermolecular attraction. So whenever we compare them with other, for example, within the same groups, let's say we have group 2, period 2, period 3, period 4, period 5. So we have the period 5s. As you can see, once we have more masses, boiling point should increase. That's for sure. Also, we can see the same trend in group 14, group 15, group 16. But you see this, we have these three elements, even though they have a lower mass than their other group members, because they have, let me write in here, hydrogen bonding. Because they have hydrogen bonding, it makes it stronger. So that's why they have higher boiling point. But for example, whenever we go down the groups, even though the masses increases, but we have their boiling point decreases. So only these, because of this hydrogen bonding, they have higher uh, boiling point. So let's compare H2O. Let me write in here H2O, and let me write H2 tellurium. Group 16, both of them are group 16. Both of them has, let me write dipole with their counter elements. So let me write H2 tellurium. This one is a dipole because we don't see any oxygen. This molecule is polar, but we don't see any fluorine, oxygen, and nitrogen. This is just a dipole molecule, but this one is hydrogen bonding, because in one side we have hydrogen connected to oxygen. In another side, we have oxygen. Please don't forget that. Also go through these simulations. Now let's quickly discuss about this worked example. So what do we see in here? Whenever you see the molecular elements carbon, hydrogen only, remember this is non-polar. If it is a non-polar molecule, again, whenever you see carbon, hydrogen molecules, they are all non-polar. So if they are non-polar, it means that we cannot have dipole-dipole or hydrogen bonding. So this is London dispersion forces. In here, we have carbon hydrogens, but we have an oxygen electronegative element. It means that polarity will be, so it will be dipole-dipole. Why it will not be a hydrogen bonding? Let me explain. So I'm gonna open the structure, carbon. If we write the Lewis structure of that, H, 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 H. So just I followed the order, CH3, CH2O. You see in here, what did we say the condition for hydrogen bonding? Oxygen. In one molecule, oxygen should be connected to hydrogen, yes? But where do we have hydrogen in here? Oxygen is connected to carbons in both cases, so it cannot be hydrogen bonded. So, but it's a dipole-dipole because this is sigma negative, so we have this sigma negative molecule. Let me complete the dipole too. So because of these non-bonding electrons, the shape will be different. So it will be a polar molecule, so dipole-dipole. Please go through these examples too. And we will be working on these practice questions during the lesson. But before the lesson, please go through these practice questions before the midterm exam. So this is the finalizing point. By the way, these three London dispersion, dipole, induced dipole, dipole attractions, they are van der Waals. They are van der Waals called. But all of them are in van der Waals except hydrogen bonding. And the physical properties of covalent compounds, I will be providing another video, YouTube video for that. Thank you for listening.